Okay, so our session is actively being recorded. And for those interested in the recordings, I'll try to load them on a link and then you go access them on that link. If you have data related challenges, I know some of you are regularly around the campus. I could deal with the coordinator who may come, pick them up, and he shares them with you. Given that they are really of some significant size. But otherwise, I'm going to share a link with you guys. It's called File Media. I can upload these recordings there, and then you have to go there and again download them, which would still be a money-related kind of challenge, given that you need again to buy data. Else, if you have I think like 2 contacts of coordinators who can easily stop by on appointment. I could let them come and then I pass them on to them and then they share with you. So we have those 2 alternatives. I'm sure we will agree on the most appropriate method to use to get those. Right. So let's have a very quick review of what we did last time, and we push forward. I'm sure you're still fresh. We looked at some theorems here and the definitions. We understood discontinuity and the sectional continuity, and we saw what this actually implies. We looked at applications related to that in the examples we discussed. So there is a small proof there. And we looked at powers of T. We discussed this quite a lot, and I had an exercise, rather a test that I had already prepared, but people were not ready. Hopefully, maybe by the end of today's lecture, perhaps some of you will be ready. I'm yet to see or to know if people will be prepared. Then we looked at an example. This is what we used to demonstrate that a sectional continuity in terms of a piecewise function. So we discussed this. I also illustrated this in terms of a Laplace of a given function, and then we also looked at the inverse. And in our attempt to understand the inverse of a Laplace transform, we demonstrated using this function here. This was derived from this, and this was after understanding the Laplace of generally a t to the n if a function is of that general format. Okay, so we looked at that basically last time, and we went further and we discussed all of this. That was a demonstration of sectional continuity. So we looked at this function, and here all we did was a few tips on how to integrate, and we played with some concepts of calculus 2, that is integral calculus, which is still fresh in your heads, guys. So, and I told you in this course we'll borrow heavily from calculus 1, calculus 2. You did the is 1, and you have also done dynamical systems. I'm aware of that. So we are going to be borrowing heavily. Most of those are going to be used as prerequisites as we move along. Okay. So we looked at this and we said, if you have something like a piecewise function such as this, and if we want to compute the Laplace transform of that, we said we can just split up this, since this is from 0 to 2, which was that 0 to 2, and then we had t greater than t moves from 2 to infinity. which is this one here. We said, okay, we can bring in an identity, and we introduced that identity, which gave us something like this here. This, of course, would cancel, and then we combined. Since this was 2 to infinity, 2 to infinity, we wanted to run this from 0 to infinity. So we combined this and this. We combined this term. We combined this term here with that term, which gave us this one here. And then we took this term with that term, which ended up with, which gave us that term there. So since this was 2 to infinity, we changed, we redefined the limits here. And redefining limits is very easy. Since this is in t, the whole idea is how does this 2 go to a 0? The only way a t can go to a 0 is you redefine, and if you have a certain x which is a t, and this is a t minus a 2. You know that when you are changing limits and you throw here a 2, if t is 2, then x will be 0. You've already redefined the lower limit here. And of course, if this is infinity, it remains infinity. So there is nothing big here. Just look at the lower limit that you want to go to a 0. This one you already know from your integral calculus, so I don't have to delve much into that. So anytime you bump into something like this and you want to redefine this with respect to the definition of a Laplace, then you can just introduce a variable. Here we introduced the x. And then after doing that, we ended up with this one running from 0 to infinity. This one was already 0 to infinity. And there what remained was ordinary integration. And that's what we did. All right, guys. So this is what we did to review. This is what we did to, this is rather what we accomplished last week. And from that, we concluded that our solution was actually this statement here. That's what we did. And from that, we went further, and we went further, and we said that for other functions, it's the same story. This work I left you to do, there is nothing big here. We already know the definition of a Laplace transform. And given that we are already familiar with the definition of a Laplace transform, which is the integral from 0, this is to infinity. And of course, you have e minus st f of t. This is f of t with your dt there. So all you need to play with in this new example, or rather the various examples that follow after here, it is the ft. So in this case, you have your ft, which is ebt, that one there. So substitute, you integrate by parts, you will get this one here. So it means once you have a function, which is e to the bt, and then you end up with this, then you can easily get the Laplace transform of that function. So what would this mean? That if I have, if I'm told to find the Laplace of a function, say e to the minus 3t, is that okay? And you can just conclude that the Laplace of this function will simply be 1 over s, and this will be plus, this is plus 3. Remember, this is minus. So since this is minus 3t, the original function was a positive here. If you look at that one there. So if it is positive, this was minus b. Since now my b is a minus 3. If I substitute it here, it becomes a plus 3. So the Laplace of this function is 1 over s plus 3. So there is nothing big in that, okay? And then we also went further and we said that we went further and okay. So if you go ahead now in terms of other functions, so this is some story. You can go and do all of these. You have your ft is e to the power that, and of course here when we say s greater than b, it's to make sure that the solution we have is actually defined, and that's why we insist on that. Okay, so I told you can go through all of these. There is Laplace here. This one we have already looked at it. If you want, you can stick to the method. Solving this, you have now two options. You can go direct. This is a direct integration, which give this one here. If you compute this directly, piecewise, this is 0 to 1, and then 1 to infinity. If you don't want to use this approach here, you can go back and you use what we have discussed here. And you redefine what we have there with respect to the definition. So we have already looked at that. So you have two options and the answers must be the same. So this number here, you can use what we discussed last time, which I've just reviewed, and you could restrict yourselves since the functions can easily be integrated. Okay, powers of product, same story here. So in this case, you now have ft. This is your ft here. Hopefully we are together. So this whole ft here, it's what you are going to multiply with the e. So you basically have t to the n. Then you have this is e to the power bt. And you now bring in the one over the definition, which is e to the minus st. You have a minus st here. My mouth is a little bit rough today. I don't know why. Let me try to use a pad. Hopefully it will be faster. Okay, so you have this, and basically this is what you're dealing with. Now the bases are the same. You deal with the powers. That's why you see you have that part there. This one comes from that. You can take the t out is common, then you have s minus b with a negative out. We are trying to regularize this because this would simply be e to the t, and then you have a certain b minus s. This is what you do have. Of course, there is a t to the n here. Okay. But since by definition, you have e to the minus st, we want to maintain that format. So if we take that s out, rather than negative out, then you'll end up with the s minus b with a negative out here. Okay. And once you do that, you remember we discussed the powers of t, you end up with this one here. All right, guys, I don't want to overly bog you down with the obvious. In that case, I'm sure the review of what we did and what I had requested you to do is explicitly clear. The good thing I'm dealing with the third years who are teachers in the secondary schools out there. Poverty was probably killing some of you. The president said your schools are going to be operational starting 1st January. Hang in there with the extreme patience. Soon you are going to be in things. So as you do homeschooling illegally, these techniques you already know. So integration, you are the experts. So go, you do all of these things. You do all of these ones. This is a playfield for you. Go do and enjoy all of these ones. Trigonometrical. I insist you just have to bring in your new FT. The FT here is cos beta, rather cos BT. You use the definition, you come to this, you end up with that one there. So you can see you already have that right there. So you have S over S squared plus B squared. So just to go and generally deal with the integration part of all of these, and you are going to have fun. The same applies to this. But here you have the imaginary part. This is just an alternative method that you can use. Once again, I don't want to bore you with the obvious, which would be equivalent to bogging you down. So all of these methods, this is like a buffet. Choose what you are comfortable with. This is like a ceremony and there is plenty to eat. You choose what your stomach can handle. So any method you use of these three methods, it will give you the correct thing. And from that, we can look at some examples here. These examples are obvious. Why are they obvious? We've looked at sine t. So sine pi t, remember we already have that sine bt. Just look at the two definitions here. So we have, I'll just activate this. Right. So we have already looked at if you do the necessary, you come up with this one here, which we have already got. This one we have done together. So since the Laplace of sine bt is this, from the integration by parts and all that I have just demonstrated, now we are saying, can we find sine pi t? So what is b? If you compare this with this here, the pi is the b, so the Laplace of sine pi t, where there is a b, you throw there a pi. That is pi s squared plus pi squared, finito. That is the answer. Then we have the Laplace of cos negative 3t. This is what we have, but remember we have already demonstrated up here that if you have the Laplace of cos bt, that is this one right here. What is that? If you have the Laplace of that, we can compare now that one with our function here. That is the ft. So in here it was cos bt, but now our b, the b is now minus 3. So that is b is minus 3. Since this is s, rather b over. So since it is sorry, I'm on cos. Cos is s over s squared plus b squared. If you square this negative, you get a positive. That's why negative 3 squared here will give you a 9. And squaring the 3 gives you 9. And we are saying from this derivation, we conclude that the cos of minus 3t is generally that one there. All right. This is good. You guys, I am sure you are scooping A's in this course because everything is as direct as demonstrated. Now in here, just give me a second, guys. A second, please. Okay, sorry about that. We can now resume. Okay, so I don't need that. Okay. Okay. Still. Maximize this. Okay. All right. Sorry, I had someone who was making a brief inquiry here. Right. So what I was saying that with respect to this, guys, remember we have already looked at our derivations. We looked at cos. We've already said that cos is, we've said our cos is s over s squared plus b squared, and we have also looked at sine, which sine we have already derived. So how do we compute something like this? First of all, there is this one here is quite direct also. Remember, we have already said that sine bt L of sine, since L of sine bt is this is b over s squared plus b. This is b over s squared plus b squared. Okay, now let's look at this one here. So if you look at this, same story. So since this is sine a half, it means your b is a half. So the b is a half. Then it means that b squared is actually 1 over 4. So that's why you see if you square the b squared, there would be b squared now here. We simply square the half, which is a quarter, which is this a quarter here. That is that a quarter there. And then it is b, the b is this a half here. I hope I'm clear there. Okay. Then we also have, so we can, if I remove this, and right. Then what about cos? Cos, we have already said that our cos is cos L of cos. This is BT. This one we have already looked at it. This one has already given us our s over s squared plus b. This is s over s squared plus b squared. Okay, so if this is the case, now here, what are we looking for, guys? Remember, we talked of the Laplace transform. We said that last time we said that if you have L of ft, we said this is the same as f s. Remember, in the definition, we have e to the minus st. So that's why we have fs. And it means if we have this, then we can look at the Laplace of a given transform, and we can also look at the inverse Laplace transform. So in this case, we have a certain function that gave us this here. So the question is, how do we work backwards to get that function? And this is exactly what we are doing. So we are moving from fs because this is fs here. That fs is what we have. So the question is, how do we move from fs and we go back to ft? We want to go back to this ft here. That is now the inverse. So we are looking for L, the inverse of the given Laplace function. This is fs. So you want to go back and you find the Laplace, the inverse Laplace transform. If you have this, then can we work backwards and we get the ft? So that's what we are trying to do here. And in doing that, we can use our definition and we can straight away get there. And how do we accomplish that? We can get that one right here. So we are saying that I see a lot of things in the chat. Hopefully you guys can hear me. Oh, by the way, before I forget, as soon as this session times out, guys, just relog in again before we lose. I'm not even seeing my countdown. Okay, I'm remaining like with 3 minutes to end this session. So let's finish this example and I go through the charts before this session goes out. I hope you can hear me. Okay, the 3 minutes are enough, right? So we have this. So if you split up this, you split up the numerator. So if you split up the numerator, splitting it up will give us the 2. That is this one here. Is that okay? And then we also have this one here. So if you look at the splitting up of this here, so this is equivalent to that under the same denominator, then we use our definitions. So in here, since we have s over s squared, now you just have to associate this one in red with that right there, because for cos it is s over s squared plus b squared. Now you can throw the 3 out, so I'm dealing with this one here. If you take the 3 out, you remain with s over s squared plus 5. But remember the definition is b squared. So since it is b squared, what you have is 5. So, but I know that if I have root 5 and I square this root 5, this actually gives me a 5. So since the denominator here is b squared, remember this is 5 and our denominator is b squared there. I can now write the 5 in terms of a root. That's why we are saying, let it be s over root 5. Now it means that my b is root 5. So I end up with a b, which is a root 5. The 3 here, I have thrown it out. So I have s over s squared plus root 5 squared. But this root 5 is actually the b. That's why from this, I end up with 3 cos root 5t, which is the answer there. And then for the second part, I have this 2 over s squared plus 5. But remember, 2 over s squared plus 5, still this 5 is root 5. But because it must be, according to this definition, only b, I have a root 5 over a root 5. Remember, if I have this and I have that one right there in the denominator, then it means this will cancel with this. You remember the identity form we're talking about. So since this is the case, I introduce a root 5 over a root 5. Why? Because this is b. So my b here is the root 5 over root 5 squared. So, but since this root 5 was not originally in here, it means I must also take the root 5 in the denominator so that this cancels with that new introduction there. So we incorporate root 5 over root 5. Then I take the 2 out. Then I end up with the root 5 over a squared root 5, which is 2 over root 5 sine of